Okay, so he's excited about the lesson. You can tell because he's purring and drooling all over my laptop. So he's super excited. This lesson will be the second part of Unit 3, Lesson 2. And yes, I know. You're excited. It's going to be the second part of the lesson. And it's going to cover solving equations by square roots and then imaginary roots when you're looking at graphs. And we'll try to tackle the last of those objectives if I am able to get to my keyboard anyway. So we've already looked at solving equations by factoring, okay? And so I did want to review an example of that just because I know that it tends to be a bit of a weaker skill, and it's just one of those things that we can't really go over too much. So when you're solving an equation by factoring, the first thing you need is you need to set one side equal to 0. And that's because the strategy that we use when we're solving this is the zero product property. So whenever you're solving an equation by factoring, that's the direction you're going to go with it. And so in order to use that property, you do need to have the 0. And then what you need to do is you need to factor the other side. Okay, whatever that happens to be. Usually it'll be the left side that you'll be factoring. So on this particular example, you'll notice that we already have the 0 on one side, so we don't have to worry about getting the 0 on one side. So we can launch right into factoring on this particular problem. So I'll go ahead and set this up. And we have 2x squared in the upper left, and we have negative 4 in the lower right, and we have that pesky leading coefficient. Now I'm reviewing the leading coefficient in the example, but on the ones that I'm going to ask you to do, because I'm actually trying to get you to see something else. I'm not going to muddy up the factoring with the leading coefficient, but it's not something that we can afford to forget. So we do 2 times, now it's technically negative 4, so we're looking for things that will multiply to negative 8. I tend to get a little bit lazy about that. And then sometimes it comes back to bite me, as you saw a couple videos ago when I had that mistake in the middle of it. So we're looking for factors of 8, and 8 factors into 1 times 8 and 2 times 4. And then in order to make sure we pick the right pair of factors, we're looking at that negative 7. So the 2 and the 4 can give me either a 2 or a 6, depending on whether I'm adding or subtracting. But the 1 and the 8, I can get a 7 from that, and I can get a negative 7 if I use a positive 1 and a negative 8. And then those need to be my x's, okay? And then I like to look for the easiest common factor that I can find. And the easiest common factor I can find, at least this way, is right here. Try to avoid the negatives if I can. So we have 2x squared and 1x. What do they have in common? They have the x in common. And then from that point on, most of the rest of the problem is pretty easy for most of you. So what times x would give me 2x squared? That would be 2x. Looking in the upper right, you have x as the height. So what must be the width? Well, it's got to be 1. And then you can use either of the bottom boxes. Okay, like once you have that first one, you can do this in any order you want. Okay, you don't have to do it the same order I'm doing it. But 1 times what would give me negative 4? Well, that would be negative 4. And then the way you know if you've done it correctly, all 4 boxes are going to work. So 2x times x is 2x squared. 1 times x is 1x. 1 times negative 4 is negative 4, and 2x times negative 4 is negative 8x. And that's how you know you've got all the pieces the right way. So this factors into 2x plus 1 and x minus 4. Now that 0 is still there, okay, because what we're doing here is we are solving, and solving means you're finding the solutions. You are finding the values of x that will make that equation true. It is different from if the directions just asked you to factor. If the directions just asked you to factor, then you would be done with the problem, but this is solving. So we know from the zero product property that 2x plus 1 is equal to 0, or x minus 4 is equal to 0. And then I can add 4 to both sides. So one of the solutions is x equals 4. The other one requires a little bit more work there. We subtract the 1 from both sides and then divide by 2. And don't let that fraction freak you out, okay? It is just -1/2. Okay, and so this problem has two answers, x equals -1/2 and x equals 4. Okay, and so that is something we've already looked at, but I spent 5 minutes reviewing it because it is important enough that it is worth 5 minutes to review. Now we're going to look at another strategy, okay? This strategy is just using a square root. So we discussed in the previous lesson that you've got like squaring, and then you've got square rooting, and essentially what they do is they undo each other. Now there's going to be a little bit of a hiccup here that we do have to keep in mind that used to bother me really bad when I was in high school. It does not bother me as much now. I feel like I understand it better now, but it bothered me a lot when I was in high school. So it stands to reason that if you had, say, an x squared, that you could use a square root to undo the squaring and get back to the x, okay? Now, there's a reason we don't cover this a whole lot or stress the solution, and that's because of this question right here. When does this strategy work? Okay, and it's got a super narrow answer. It only works when b is equal to 0. That is when there is no x term. So you figure like a lot of quadratics have what we call an x term, okay, which is that term right there. So you've got the squared term or the quadratic term, the x term or the linear term, and then you have the constant term. This strategy only works when b is equal to 0. So here it's equal to 2, but it would only work if the b value was equal to 0, because what's 0 times x? Well, that would be 0. Now you might think, well, how many equations do you ever see like that don't have an x term? The answer is not that many. You do see them, they do exist, which is why this is a strategy, but you don't see them a lot. Okay, and so when teachers are kind of cramped for time and we need to get like the most significant material out in the shortest amount of time, we will tend to skip strategies that are kind of narrow in their application. We'd rather have you get really good at a strategy that's going to work all the time or most of the time than to try to do like lots and lots of strategies, but like they don't always work, and then your brain kind of gets cluttered with it. So here are some examples of equations that you could solve with square roots. So I think I just had one like this. All right, so x squared minus 5 equals 0. X squared minus 5 equals 7. Okay, that would also work. Now you would have to move some stuff around a little bit, but you will notice as long as there's no x term, you're okay. You could also use it for things like this, which is why I'm introducing it here. Okay, which is why I'm introducing it here. So square rooting only works when you don't have a b term, you don't have an x term, okay? Technically when b is equal to 0. So we're actually going to compare this. I want to do a problem two different ways, just to kind of show you how the two ways compare to each other. It reviews one of the older ways, and it will help you see a little bit of like what can make the square root method a little bit tricky here. So we have x squared minus 9 equals 0. Now what I want you to notice first off is that this is the difference of two squares. I am pausing to give your brain a chance to kind of recognize what I said there. It's the difference of two squares. So you can use that, factor that using the area model. Most of the time though, I won't. Most of the time I will just remember the pattern for how it factors. it factors into conjugates, where you would take the square root of each, and then one of them is a plus and one of them is a minus. And then you would use your zero product property. Okay, and then you could solve these. So this one you would subtract 3 from both sides to get x equals -3. And this one you would add 3 to both sides to get x is equal to +3. So you can clearly see that there are two different answers. So -3 and +3. And the reason you have two different answers is because when you square them, you would get +9 both times. So 3 times 3 is 9, but -3 times -3 is also 9. And so both of those would work. Okay, now a lot of times teachers actually want you to solve the problem this way because we want you to remember how to factor the difference of squares and we don't want you to forget. And so a lot of times teachers, like from an educational perspective, will kind of steer a problem in that direction. Okay, and obviously it works. Now we can actually though use another strategy for this because it fits that template of there's no x term in it, or our b value is 0. So the way that would work is we would do this. We would add 9 to both. Hang on. We would add 9 to both sides, and we would get x squared is equal to 9. Now from this point, you can kind of reason your way out and then say, okay, well, what squared gives me 9? And you can reason that out that it would be positive or -3. So one of the reasons teachers don't use this method a whole lot is because students will often miss the negative answer. And so students will, oh, what squared equals 9? 3. And yes, like it's true. 3 is one of the answers, and then they'll miss the other answer. And you know that in order to solve the quadratic, you have to get both of them. Now, sometimes you might do a little bit more work there. You might show this with the square root. Now, here's the part that bothered me when I was a student, like really, really bad, is if you just have the square root of 9, the answer is 3. Okay, just 3. However, if the square root of 9 came from a problem like that, and then you were square rooting it as part of another problem, you had to put plus or minus in front of the square root. And I remember being in, it was pre-calculus when this became an issue, and it bothered me so bad because both of them, you were solving something by taking the square root, and the fact that one of them you only use the positive and the other one you had to make sure you included the negative really, really, really bothered me. Now as a teacher, it doesn't bother me as much because I think I see better where the problem is coming from, that because we're looking for what squared gives me 9, as opposed to just like x is equal to the square root of 9. Okay, that's not quite the same problem as x squared equals 9. That it really, really, really bothered me as a student. Like this one is just a 3 and this one is plus or minus 3, and it has to do with that squaring. Okay, so that's comparing the two solutions. One of these is not better than the other. They're both really good. This one is a little bit more error prone in that people are prone to forget the negative. This one, you do have to go through the factoring, which means you do have to remember more about your factoring. So you can kind of pick your poison on that one. So what about this one? Okay, and this is why I'm going over this now and just saying, okay, let's take a moment and let's do this strategy right now. So this one is not the difference of squares, and you know it's not because it has a sum, it has a plus sign. Difference means subtraction. This is not subtraction, but it is two squares. This is called the sum of two squares, and generally it is considered not factorable. Now, as we will see, there is a way that you can get some factors out of this, but you probably don't want to. And in a standard Algebra 2 class, I think it's debatable how worth it is to go through that. But there are classes, potentially an honors class or a pre-calculus class, where yes, you would want to kind of move through that a little bit more. But this one, we would opt to solve it using the square roots. And so instead of adding 9, I am subtracting 9. And that brings us here, which should look familiar, and it kind of brings the last lesson back around to this one. If you're wondering, where is she going with this? Now we have some number squared gives me -9. And at that moment, you realize this is an imaginary number. Okay, if we have to have x squared and it has to equal a negative. Now, if you can reason it out from here, okay, if you can reason this out and think, okay, well, 3 squared gives me 9 and I squared gives me -1, so it would be 3i, or technically plus or minus 3i, I'm okay with that. For most of you, though, you probably want to do the workout on it. Okay, now here's the catch, and that's why we started with the other one. You do need to remember the plus or minus, just like you would have to as if it was a positive. Okay, so you do need to remember that. The square root of x squared is just x. And then we have the square root of -9, which we've looked at before. That's the square root of 9 times the square root of -1. Which is the square root of, yeah, there we go, which is 3i. And so your answer is plus or minus 3i. Now, just to make sure that we remember like our definitions of solutions, remember the solution to an equation is the value of the variables that make the equation true. That's what a solution is. That's what it always is. So if I take 3i and I plug it into that equation, or if I take -3i and plug it into that equation, they should both work. Well, what is 3i squared? That's 3i times 3i. Now remember, this is all multiplication, so you can multiply in any order that you want. 3 times 3 is 9, and I times I is I squared. But what is I squared? Well, I squared is -1. And so you have -9 plus 9, and it is 0, and it makes the equation true. And the same thing would happen with the -3, because -3 times -3 would give you +9. Okay, and so it works, and both the positive and -3i work on that one. So there's that. Now here's what I want you to do. I'm planning at this time, it does not exist at the time I'm recording this, but to just on your notes for the class to write down each of these equations for you. And I want you to solve each of these equations, okay? Now, for some of them, like you do need to solve them by factoring, okay? If you have an x in it, you have to solve it by factoring. If you don't have an x, you just have the x squared, then you have the option of using the square root. Now, if it's the difference of squares, which number 4 is, then you would have the option of factoring it also. Okay, so you're going to solve each of those 5 equations, and then you will do this. Now use Desmos to graph each of these equations. Okay, and we're going to look for patterns. That's what we're trying to do here. We're trying to look for some patterns. Like, we know that math is consistent, and we know that the equations and the graphs are related to each other, because we can use those graphs to find all kinds of things about those equations. Okay, and so we know they're connected. Here are the questions on a separate piece of paper. Answer the following questions, and you're going to turn them in. Now, if you're watching this from home, there's no reason why you can't do this entire assignment from home and just upload it. Okay, no reason why you can't do that. So which equations had x-intercepts, roots, or zeros that you could see on the graph? Remember that these are all synonymous, okay? X-intercepts, roots, and zeros. are all like the same thing. I could have said which equations had x-intercepts that you could see on the graph, which equations had roots you could see on the graph, or which equations had zeros as you could see on the graph. Now, which equations did not have x-intercepts, roots, or zeros that you could see on the graph? Okay, in fact, we could say they didn't have x-intercepts at all. Okay, you didn't see them on the graph. So which ones had the ones that you could see on the graph and which ones did not? And then here's the critical question. Based on your answers to the equations, what does getting imaginary answers mean for what the graph will look like? So if you're solving an equation and you get imaginary answers out, what does that mean about the graph? Okay, and that's the one that I'm really going to be paying attention to. Okay, but you can't get that one right if you get 1 and 2 wrong. All right, so you need to make sure that you're tending to all parts of this, and then that will be your assignment for this lesson. Okay, so I hope that was a good little lesson, a little shorter than usual because it's piggybacking on the previous lesson. And then you know how to find me with questions.